speak about the propagation of a pulse through a one-dimensional random medium. But also this situation is quite simple from the PD point of view. It's already quite complicated from the probability point of view. This will allow me to review a certain number of phenomena that can happen during this wave propagation, namely 4 phenomena. So the most simplest one that I will speak about is simple effective medium theory, whose purpose is to compute the effective velocity of a wave traveling in a strongly heterogeneous medium. And then I will go deeper and deeper into these phenomena. Namely, I will consider first the deformation of the front pulse as it propagates deeper and deeper into the medium. So this is a theory which has attracted a lot of attention, both from physical point of view. So actually, this theory was first introduced by geophysicists, Fourier Transform, and it was progressively understood by mathematicians. And only in 1994 we get the first mathematical proof of this problem. Then I will go in another issue, which is, okay, on the one hand, you have the coherent wave, which is propagating into the medium, which emits some radiation because it experiences multiple scattering. So progressively, this coherent wave is transformed into incoherent wave fluctuations. And I will then address the statistical description of this incoherent wave fluctuation. And eventually, I will speak about the most interesting issue, the one about which I have spent the last couple of years with these collaborators, the time reversal of waves out of media, which consists in recording noise, just incoherent waves, time reverse these signals in a computer, in memory, and re-emit these signals into the medium. And then, very surprisingly, from only noise, you will regenerate a purely coherent signal. And this has very nice applications, in particular in imaging and telecommunications. I will speak about imaging applications and maybe a few words at the end of the talk about telecommunications. So first, what is a random medium? What do I mean by a random medium? The problem I deal with is wave propagation in a heterogeneous medium. A medium whose parameters have very complicated spatial variations that I do not know. For instance, in applications in geophysics, you do not know exactly what is a medium, what is the exact description of the Earth's crust. So you have to do some modeling. So the stochastic modeling consists in describing this medium as a realization of a random medium, that is to say, a set of possible media described statistically. So, what are the key ingredients of this stochastic modeling? First, it should take into account all the information that you have about your medium. For instance, you may know the typical value of the parameters of the medium, the typical fluctuations, the standard deviations of the parameters. Maybe you know also the correlation length of the medium, the polar spectral density. You may have different information. So this stochastic modeling should take into account all this available, all this data. And as you do not know everything, you complete the description by a statistical modeling. For instance, if you know only the mean and the standard deviation of the fluctuation, the natural statistical completion consists in considering that the medium is a Gaussian process with the mean and the standard deviation that we need. But maybe it's not well suited. For instance, if you know that these parameters are positive values, this may be physical parameters, density, index of refraction, I don't know what, then you know that these parameters are positive valued, then this is a piece of information, and you shouldn't take a Gaussian description, because the Gaussian random variable may take values between -infinity and +infinity, so definitely it's not well suited for such a problem. It's not well suited because first you will violate the physics, and second, you do not use a piece of information that you have, so you are not going to be efficient. So this is the stochastic modeling. So then you face the following problem. Now you have a wave equation, so partial differential equation, with random coefficient. You know now you have a statistical description of this random coefficient. And what you want to compute is a statistical distribution of the wave propagating in this medium, that is to say, of the solution of this partial differential equation with random coefficient. And this is a highly nonlinear problem, even if the PDE is linear. When you go from the statistical distribution of the coefficients of the PDE to the statistical description of the solution of the PDE, you face with a very highly nonlinear problem. So that's something very important to remember. And the question is, what can we say about a wave propagating in one typical realization? If you think that in your physics, you have only one Earth, the one that we live on. So what does it mean? A random description. You have to do very clever analysis. First of all, I will try to show you that the typical analysis, which is a mean field approach, you compute the field average over all possible realization of the medium, is usually very misleading in the sense that you will get an exact result for the mean field. But the mean field is not at all the typical, is not at all representative of the typical field, the field that we will observe during a typical experiment. Which means that you have to compute the complete statistical distribution of this random wave to try to extract what I call statistically stable quantities. That is to say, quantities, some particular characters of the wave, that depend only on the statistics of the medium and not on the particular realization. So you have to look after the statistically stable quantities, which are the ones which are really important, especially from the point of view of imaging. And you will find these statistically stable quantities only in some limit regimes, in some asymptotic regimes. That is to say, you have a problem where you may have different length scales. You may think the typical wavelength of the wave, the propagation distance, the correlation length of the medium. You may have different length scales. And you can try to study some asymptotic regime, for instance, the case where the wavelength is much smaller than the propagation distance. Then you will try to analyze these problems, this random partial differential equation, in some asymptotic regime. You will get a limit PDE, which will be interpreted as protected from some differential equation, and we will try to analyze this PDE. So, roughly speaking, your analysis can be split into 3 steps, but which are closely related. First, modeling. So first, find what are the relevant equations. So this is typically a wave equation. You have to describe statistically the medium parameters, and you have to identify the different scales present in the problem. And then you do your asymptotic analysis. That is to say, you try to separate the scales, if it is possible. What are the small parameters which you can observe in this problem, and you apply some limit theorems that I will describe. Eventually, you get a limit problem, and you try to analyze within this limit problem the physically relevant quantities. So let's go. First, I will start with not mathematics, but physics. So I will speak about an experiment carried out by physicists. So no mathematics for the first time. So this experiment was carried out at the end of the 19th by Matthias Fink, an academician which is working in Paris. And this guy built a very, very special device, which is called the time reversal mirror. So what is this device? It's an array of transducers. What are transducers? These are very small devices which can be used either to record an acoustic signal or to emit an acoustic signal. So they can be used both ways. And we carried out a series of experiments. Each experiment is done in 2 steps. First of all, you have somewhere a source which is emitting a very short signal with very short pulse, which is propagating in some medium. Your time reversal mirror is then used as a recorder. So you record back the waves into the medium. The problem is, what will happen? So what Matthias was expecting, of course, is that you will have the refocusing at the original point source. And indeed, that's what you observe. So here, this is what you observe. Yes, this is the original pulse source. So the source is emitting very short pulse, 1 microsemon. This is what you record on the time reversal mirror. So your medium is highly scattering. There is a lot of multiple scattering in the medium, so you get a very noisy signal. So we see the duration of this noisy signal is very long, and then you show a piece of it. Then you time reverse this signal in the memory, send it back into the medium, and you get a refocusing. And okay, Matthias thinks, well, okay, this is normal. But the point is, the refocusing is all the better as the medium is more scattering. But if you see, this experiment does not work in homogeneous medium. And the more scatterers you put into the medium, the better the refocusing is. Okay, so the main point of my talk will be to explain you what's going on. So let's go now to mathematics. So as I told you, I will consider a very simple situation from the PV point of view, the acoustic wave equation in a one-dimensional world. So that's quite simple. So the medium is characterized by two parameters: the density of the medium, the bulk radius, which is something to do with the compressibility of the medium, and you write the propagation equation for the field, which consists of a pressure field and a velocity field. So these two guys satisfy these partial differential equations. So I just point out that in such a problem, often you have three length scales. The correlation radius of the medium, which is the typical length scale at which the parameters of the medium are varying in the medium. You have some length scale which is associated to your initial condition, which is the width of the pulse. And you have the propagation distance. So during this talk, I will play with these parameters. So first, okay, what happens in homogeneous medium? So one-dimensional wave equation with constant parameters can be decomposed into two transport equations. Just have to introduce the two Riemann invariants in your system, that you could be weighted sum or differences of your velocity and pressure field, and then you get well-known answer that your wave equations are equivalent to a set of two transport equations, one for the Riemann invariant which is going to the right, and one which is for the Riemann invariant which is going to the left. And which means that, okay, you can play with that. And for instance, if you choose an initial condition which is such that B is 0, initially 0, then remains 0, and you get a pure right-zone wave propagating over arbitrarily large distance. Oh, that's this. So let's go the thing progressively, just to put a picture. What happens when you have an interface? So now my medium is not homogeneous. Now I have two homogeneous half spaces with different parameters, C and zeta, which are the parameters of medium, sound speed and impedance. You have an incoming wave, so it's incoming from a homogeneous medium, so it's going at constant velocity, and then it will experience the scattering by the interface, and what you get is a transmitted wave and a reflected wave. Here the transmitted wave is going faster because the velocity in the second part of the medium is larger, so you get this. So that's very easy to compute this type of solutions. All that you have to do is, I know the form of the solution in the left half space, I know the form of the solution in the right half space by the Riemann invariants, and I just write the continuity conditions for the pressure and velocity fields. You solve and you get the solution. So now what happens with two interfaces? Then it becomes a little more complicated. At the beginning, same story. This incoming wave is partly reflected, partly transmitted. The transmitted part experiences a new scattering by the second interface. So it's partly transmitted, partly reflected. But this guy, which is partly reflected, once again experiences a new reflection by the first interface. So you get transmission, reflection, and so on, and so on, and so on. So this is typically what you observe in a simple heterogeneous medium, just a layer embedded in homogeneous fast spaces. But we can go in a more complicated world. Now consider a stack of, here I think there are 3,000 layers. So you do the same analysis as before, so you can imagine multiple reflections taking place all over the place, and you get this picture. So you have your incoming wave, which is entering into your medium, and you have multiple scattering, multiple reflections, which are going out of the medium, and your pulse is propagating into the medium. So here the random medium is very simple. Actually, this is just a stack I told you of about 3,000 layers, consisting only of two materials, two alternating materials, and only the thickness of the layer are randomly varying. They are different from one layer to the other one. People are comfortable in probability. I can tell you the thicknesses of the layers were taken as independent random variables with exponential distribution. That describes completely your random medium. So this is a typical picture that you get, and this is a picture that I want to explain. First, also the medium is highly scattering. You can see that your wave looks like it propagates in a constant medium in the sense that the velocity is almost constant. Here you have almost a straight line for the front pulse. So this is the main issue, the first issue I want to discuss, the effective medium theory. So in this effective medium theory, you have an input pulse that you send into a slab of random medium. So my slab of random medium is going from 0 to L. I have this input pulse, a right-going wave. I have the wave equation, the density of the medium, the bulk modulus of the medium, and I will assume that my random medium has a correlation length which is small compared to both the support of the incoming wave and the propagation distance, so that I can introduce a small parameter epsilon which characterizes the scale of variations of my medium. So this is the situation I want to consider. The correlation of the length of the medium is much smaller than the wavelength of the wave and the typical propagation distance. And I want to analyze what happens in this regime, and in particular, in the limiting regime where epsilon goes to 0. Can I describe very simply the limit of the wave as epsilon goes to 0? So to do that, I just explain in a few words how it works. One key ingredient is the Fourier transform, because your medium is only varying spatially, not with respect to time. So you can take a Fourier transform of this set of partial differential equations, and what you get is very simple. You get a set of two ordinary differential equations for each frequency. So that's very easy. So in some sense, the problem is greatly reduced from the analytic point of view. You have gone from a PDE to ordinary differential equation. This is only true from the analytic point of view. These systems are uncoupled for the analytic point of view. From the probability point of view, they are not uncoupled, because in all these systems, you see exactly the same realization of the random processes rho and kappa. You have to be careful. From the analytic point of view, that's very simple. From the probability point of view, you will have to study all these equations for all frequencies together. You have to compute the joint distributions of all the solutions of these ordinary differential equations for all frequencies. But you can do that. So what will happen? Here, what you get is a system of ordinary differential equation of the form d of the unknown over dz equal something which is varying fast. So, toy model. So simple. Yeah, very simple toy model. So assume, for instance, that you deal with this very, very simple ordinary differential equation, whose right-hand side does not depend on the unknown, so you can integrate it very easily. And consider, for instance, a random medium, which is just a stepwise constant medium. Yeah, here you can see the beginning of the f of z, of one realization of f of z, so it's constant over over elementary layers with thickness epsilon. Epsilon is here 0.2. So you have here one realization of f, and here you have the solution, the corresponding solution for x epsilon. And what you get is that, okay, it looks like to increase as a straight line. Is it surprising? No, of course, it's not surprising. This is just a consequence of a very, very simple limit theorem is in probability theory, the strong law of large number. Why is it true? Because you just integrate your ordinary differential equation. Okay, so you get this representation of the solution. You will split this into two because you have some small rest. And you face with something which has this form, so a sum of a large number of independent random variables. You multiply by the integral part of z over epsilon, divide by the integral part of z over epsilon, and you look at first this guy, as epsilon goes to 0, it goes to z, that's easy. And this guy, what is it? It is the average of the sum of a large number of independent random variables. So every people who have done the first lecture in probability theory should know that this guy should converge almost surely to some limit, which is simply the expectation of your process. And so what you get is that your x epsilon converge to x bar of z, which is just f bar times z, that is to say the solution of this ordinary differential equation. And indeed, that works. If you reduce epsilon, you get better and better convergence. So for epsilon equal 10 to minus 2, you get a very nice agreement between the solution of the ordinary differential equation and the effective solution. So you have more refined versions where the right-hand side depends on the solution, the Hashminsky theorem, which was written in the 60s. I can't remember exactly when, but in the 60s. And you get exactly the same picture, that is to say, you start with this ordinary differential equation with a fast-varying components, a fast-varying random components, and you get that as epsilon goes to 0, the solution of this ordinary differential equation converges to the solution of an effective ordinary differential equation, where simply f bar of x is the expectation of this random term with respect to the random component. So this is just the analogous of the toy model I've just considered. And actually, for Marc Fourier, if I come back to my wave problems, my Fourier components exactly obey the same type of equations. So I will apply the Hashminsky theorem, which tells me that this solution, the solution of this ordinary differential equation, converge to some effective equations where I should take the average of the right-hand side. And what is the average of the right-hand side? So it means that I have to take the average of rho, that I denote by rho bar, and the average not of kappa, because what appears here is 1 over kappa, so I should take the average of 1 over kappa. So I introduce kappa bar, which is the harmonic average of kappa, which is the 1 over the expectation of 1 over kappa, which is different from the expectation of kappa. So the averaging theorem tells me that these are the correct effective parameters. And then I can introduce my effective wave equation with some effective sound speeds computed with these effective parameters rho bar and kappa bar. And then I can go back to the time domain and show that my solution of my wave equation with fast random varying components converge to the solution of this effective wave equation with homogeneous parameters. So this tells me that the effective sound speed is c bar. So you see here everything is very simple. So nice application. The sound velocity is in water, in a mix of bubbles in waters. So these are the parameters, the physical parameters for air and water. So at least you should know at least this one, the density of water, 1 kilogram per liter, and the three other ones you can find them in books. And you get the sound velocity in air and in water. So now you put some bubbles in water, and you do this computation, and then you find a very surprising result. But this comes from the theory that the effective velocity is not at all between these two typical values. It can be completely different. It can be much smaller. If you have 1% of air into water, the sound velocity is down to 120 meters per second. Because, this is just because of this guy. Instead of taking the average of kappa, you take the harmonic average of kappa, and this changes completely the picture. So here I've just done this computation. Very, very, very simply, you can do it. And you get this very surprising result that the sound velocity in a composite medium can be much lower than the sound velocities of the components of the medium. And this holds true not only in acoustics, but in elasticity, in various other fields. And this tells you that composite media can have properties which are completely different from the elementary properties of the element of this composite media. You can generate media with very strange, very fancy properties just by doing these simple computations. Okay, one thing that can be remarkable is that the average sound speed can be much smaller than the infimum of the velocities of your components, but the converse cannot be true. By a simple Cauchy-Schwarz inequality, you get that the effective velocity, whatever you do, is always smaller than the maximum of the speeds of the elementary components. Roughly speaking, you cannot go faster than light. But you can build some optical media with a light velocity very, very low. Okay, let's go back to, this was my first issue. This was the simplest one. Now we go back a little further. So what I've just shown you is the beginning of this picture. So at the beginning, this incoming wave is propagating as if it were in a constant effective medium, so with constant velocity, without deformation. But this only holds true for a propagation distance, which is of the order of the wavelength of the pulse, of the incoming wave. For very long propagation distance, you can see that, okay, the velocity is still constant, but if you compare the shape of this pulse with the shape of the incoming pulse, it's not exactly the same. This guy has been deformed with respect to the incoming wave. This can be understood very easily. You have very small radiation, which are vanishing as epsilon goes to 0, but you continuously emit some radiation. And as the total energy of the field is preserved, at some point, the energy of the front should decay. And this is what I want to address now, to go to a regime of long propagation distance. So just to come back to my toy model, this question is exactly equivalent to consider this toy model, but now to consider that the average of these random variable Fi are 0. So you center your ordinary differential equation so that the average of the random variables is 0. So this is exactly the same as before, but now with the average with 0. You apply, you solve your ordinary differential equation. And okay, what you get is consistent with the Hashminsky theorem. You get that for propagation distance of order 1, you converge to 0. You do not move. So what you have to do is to go at larger propagation distance, at larger z. And actually it turns out that the correct propagation distance at which we'll see something of order 1 is a propagation distance of order 1 over epsilon. So we'll consider this guy, which is solution of these new equations. And this new equation turns out to have an effective properties that I will study in a few minutes. So the equivalent for my wave propagation is this situation. This is exactly the same situation as before. So I have an incoming wave. I have a random medium, which is described by these random parameters, which are varying at the scale epsilon. So note that now I have put my equation into dimensionless form, and now nu and eta are zero-mean processes. That is to say, I consider that the average of 1 over kappa is 1, and the average of rho is 1, so that the mean velocity is 1, and the mean impedance is 1. So everything has been centered so that the means are 1. And now I consider a large propagation distance. I want to look at what is transmitted through such a slab of random medium after a propagation distance of the order of 1 over epsilon. So actually I will shift everything because I do not like this setting. In this setting I have 3 scales: epsilon, the correlation length of the medium; 1, the typical wavelength of the incoming wave, and 1 over epsilon, the propagation distance. I will shift everybody. I will consider that the correlation length is epsilon squared, the wavelength is epsilon, and the propagation distance is 1. So this is exactly equivalent. I've just shifted everything so that the propagation distance is always order 1. This is my reference. This is my macroscopic distance. So, and I will compute this. So I told you now nu and eta are zero mean random processes, and actually the right processes are not nu and eta, as you will see in the equations. They are m and n. The sum and the difference of eta and nu. And now you do first an PDE analysis, which is equivalent to the one I've done for the effective medium theory. That is to say, I go to the frequency domain, and I try to reduce my partial differential equations into a set of ordinary differential equations. Here there is a little more algebra because I want to center my ordinary differential equations along the right characteristics, that is to say, along the effective deterministic system. So it's a little more tricky, but you can do it. And what you get is that for each frequency, so here I have an integral representation of the reflected pulse. Here I have a representation of the transmitted pulse, the one which is going through the slab. And here you have a set of 2 ordinary differential equations describing the evolution of these reflection and transmission coefficients. And what you get is very similar to the toy model. The randomness, the random processes appear in the form 1 over epsilon m of 0 over epsilon squared, which is the perfect setting to apply diffusion approximation theorem, I mean a standard limit theorems in probability theory. So this is, I would say, just some algebra, nothing deep. Everything is true, whatever epsilon, whatever the realization of the random medium, you could do that in a deterministic medium by some way. This is just algebra. So let's go back to my toy model. I play with that. So I just consider this ordinary differential equation in this particular scaling, 1 over epsilon f of 0 over epsilon squared. So now I have a very, very oscillating medium. And remember, I had shown you the picture just before, which was actually just the beginning of this picture, where nothing happens. For small propagation distance, you see nothing. And after a long propagation distance, you see that this guy, okay, it becomes order 1. So what is this stuff? You do the same analysis as before with these new scalings. That is to say, you write the integral representation of your solution. Okay, forget about the rest, which is uniformly bounded by epsilon. And now you have a sum of a very, very large number of independent random variables, a number of the order of 1 over epsilon squared, and you have a factor epsilon in front of it. So you just multiply by the square root of 0 over epsilon squared, so that this guy here will converge as epsilon goes to 0 to square root of z. And now you have this sum, this normalized sum. So a sum of a large number of independent random variables with mean 0 divided by the square root of the number of random variables. And this is the second theorem, well-known theorem in probability, the central limit theorem, which claims that, okay, this guy converged as epsilon goes to 0 in distribution to a Gaussian random variable. So what you get is square root of z times this Gaussian random variable, which show you can enter the square root of z into the variance, that x epsilon of z converge to a Gaussian random variable with variance sigma 2 z. And if you work a little bit, but then you have to do a little deeper into the probability theory, you can prove that not only for a fixed z, this guy is going to a Gaussian statistic, but as a process, as a continuous process, it converged to a Brownian motion. A Brownian motion being a Gaussian process with these particular variants and with independent increments. So actually what you had just before, this is just a realization of a random Brownian motion. So you can go a little deeper because this was a toy model. Actually, you can write such limit theorems for more complicated equations where the right-hand side also depends on the unknown, x epsilon. So these are the typical, this is a typical diffusion approximation theorem where you prove that these processes, as epsilon goes to 0, converge to some diffusion process as epsilon goes to 0. That is to say, a process which is locally like a Brownian motion, but with a little more complicated, with a non-homogeneous diffusion matrix, with a non-homogeneous drift, and so on. So you can prove theorems for these types of equations. And for instance, there are two ways to write these theorems. Either you characterize the limit process with some infinitesimal generator, which is fine to compute moments, or you can also characterize the limit processes as being solutions of stochastic differential equations. So I don't want to enter too much into the details, but just, okay, you start with these typical equations and you end up with this equation, an effective equation. You do not have epsilon anymore, of course, this is a limit as epsilon goes to 0, where you have a deterministic part, drift, and a purely random part driven by a random Brownian motion. And you can compute B and E and A from the statistics of F. So you can even go deeper, because this is actually what you need in the wave propagation problem. In the wave propagation problem, actually, you have three scales. Yep. If you look at precisely, the random components is 1 over epsilon m of z over epsilon squared. But you can also see that I have random deterministic periodic phases, which are going to the velocity 1 over epsilon, which correspond actually to the wavelength of the input pulse. So you have three scales. 1, the propagation distance, epsilon squared, the random components, and epsilon, the wavelength. So actually what you need is to apply such a limit theorems where you have both random components and periodic components. But you can do it. Okay, this is just computations, algebra, and probability theory. And you get something which is very similar to the previous theorem. That is to say, as epsilon goes to 0, this guy converges to some diffusion process characterized by some generator or by some diffusion matrix and drifts. So you can compute everything in that case. So this is what you need for the wave propagation problem, and this is the result. If you focus on the front pulse, you get these typical results. So you need, it takes some time actually, because the previous result was written for an ordinary differential equations. To get this result, you have to consider an infinite set of ordinary differential equations. This is a little more tricky, but you get something rather simple. That is to say, as epsilon goes to 0, your pulse, your transmitted pulse, converge to something which can be described by this expression. That is to say, you have two components. You have a deterministic component, a convolution kernel, which is completely deterministic, plus a random part, which is here simply a random time delay. So this means that in this regime, as epsilon goes to 0, the transmitted pulse has a deterministic shape together with a random time delay, which depends on the realization of the medium. So this was, as I told you, first pointed out by geophysicists who just observed it without proving it, and this was proved in the 90s by mathematicians. So that was exactly what we observed here. When you send a pulse into a random medium, you observe a very slow deformation of the pulse. So here what I will now look at is just the transmitted pulse, and I plot it here. So here actually I perform two numerical simulations with two different realizations of the random medium, and I compare the two output pulses. So in dashed line you get the input pulse, so a nice Gaussian, and after traveling through the random slab, you see that this Gaussian pulse has been attenuated, it has broadened a little bit, but the shape does not depend on the realization of the random medium. For the two realizations of the random medium, I have exactly the same output shape. So I have a random time delay. The output time of my pulse depends on the realization of the random medium, as predicted by the theory, but the shape is perfectly predictable by the ODRT kernel that I have written just before. You can predict perfectly the shape of the output pulse. So this is the first example of a statistically stable phenomenon. The output pulse does not depend on the realization of the random medium, just on the statistics of the random medium. So, okay, now I have described this guy. But in some situations, you do not have access to the transmitted pulse. Think at typical applications in geophysics. You send a pulse into the Earth, you listen to the echo, which means that all you have access is the reflected waves. And when you look at these reflected waves, it doesn't seem there is anything coherent in this signal. It seems to be only noise. If you plot it, you get something which looks like a seismogram. I mean, if you have already seen seismograms, that's exactly what you get. This is the reflected waves. Question is, how can I describe these reflected signals? And for the imaging problem I have in mind, how can I extract some information about the medium from this guy? So first, I write the integral representation for the reflected waves that I've already written just before. It's quite easy to get that the expectation, the mean field, I would say, is 0. So which means that there is no coherent signals here. If you average over the random medium, you will get nothing. So you have to go to the reflected intensity to see something. So the reflected intensity, you just write the square of this integral as a double integral, and you get a product of two reflection coefficients. So let's go compute the statistics of this product of two reflection coefficients. And this is done here, and actually, this is very similar to the ODRT state theory. You write an equation for the product of reflection coefficient, and you get an equation in which the random components appear in the form 1 over epsilon m of z over epsilon squared, and the same for the process n. So once again, you will apply an approximation diffusion theorem. You will do your computations and blah, 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 and you will get that these random processes converge to diffusion processes, and you will compute, for instance, the moments of these processes from stochastic calculus analysis, Ito calculus, and so on. And what you get is eventually, with the application of this diffusion approximation theorem, the limit of the expectation of the product of two reflection coefficients. And you can go even further, so it gives you the asymptotic of the mean reflected intensity, and you can go even further. You can compute the autocorrelation function, the limit of the autocorrelation function. You will get exactly the same type of expression, sorry. And you can compute actually all the moments. And once you have computed all the moments, you have computed the complete statistical distribution, and eventually you get this result. As epsilon goes to 0, the reflected waves converge to a stationary Gaussian process, locally stationary Gaussian process, whose autocorrelation is exactly this expression, so with the function of V1, which actually contains all the information about the medium. So now if you think about applications to imaging, that is to say, you perform a series of experiments where you send a pulse into the medium, you listen to the reflected waves, and you want to extract information about the medium. How can you do that? First, I have just shown you that the process is a Gaussian process, which means that all the information is in the autocorrelation function, the two-point autocorrelation function. It's useless to compute higher order correlations because, as you know, for a Gaussian process, everything is characterized by this two-point autocorrelation function. So everything is in the autocorrelation function. Fortunately, the autocorrelation function depends on this function V1, and this V1 contains the information about the large-scale feature of the medium. So that's good, because V1 is solution of a transport equation in which the large-scale variation of the medium appear. So that's good in some sense. In some sense, in the sense that if you are capable to compute the autocorrelation function, then you can get V1, and from V1 you can invert the deterministic transport equation and get information about the large-scale variations of the medium. This is well known by geophysicists. And there is a huge literature about how you can invert, you can go from here to here. The problem is, okay, how can I estimate the expectation of the product of two reflected waves? Because I have only one realization of the medium. So what is this expectation? And then also you have a huge literature which is devoted to the computation, the estimation of this expectation from one single realization. So you can understand that doing statistics with one realization is not easy. So what you have to do is some local average for a window which has to be chosen very precisely. People have tried time-windowed Fourier transform, and actually the most efficient methods are based about wavelength decompositions methods. So you have a huge literature about how can you extract the autocorrelation function from seismic data. But anyway, it's not very efficient. It's not working, otherwise you would know that you could find oil very easily. So, let's come back. The problem is, though, that this guy is completely incoherent. So if you want to extract information, you have to do some averaging, and it's not easy. But actually, we will be able to extract information in another way by using time reversal. So what is a time reversal experiment? So the first part of the experiment is exactly the one that I have described here. You send a pulse, you listen to the echo. Oops. So you send a pulse, you listen to the echo, you record the echo, the reflected waves. And you time reverse this signal in memory and you send it back. So you take this guy and boom, you send it back into the medium and you listen to the new echo. So when you write the integral representation of this new echo, you find exactly this integral representation. You can see the original pulse shape, the window function, because of course you cannot send too many waves. You have to cut the reflected wave at some time t1. You have a phase term, and you have this product of two reflection coefficients, one of them being complex conjugated. This complex conjugation comes from the time reversal operation. So once again, you have a product of two reflection coefficients. Okay, I've done the study just before. So I just remind you that you get this effective behavior. So the product of two reflection coefficients is described by this function v1. So it's a time domain, blah, 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 blah. You do your computation, and you get that the expectation of the new reflected pulse, new reflected wave, is a convolution of the original pulse with some kernel which depends only on v1, the function which contains the information about the medium. So of course this is nice, but once again I have taken an expectation here, so I have the same problem as before. Now I do a little more, I compute the fourth order moments of the reflection coefficient, and I find that, that's strange. These fourth order moments, as epsilon goes to 0, become equivalent to the product of two expectations. So I just go a little further, and now I compute the square of the expectation of the square of the reflected pulse, of the reflected wave. I do my computation, I use this result that asymptotically, this product of 4 reflection coefficients become equivalent to product of 2 expectation of 2 reflection coefficients, which shows that asymptotically, the expectation of the square becomes equivalent to the square of the expectation, which means that the variance is going to 0, which means that the refocused pulse is a statistically stable quantity. You have something deterministic. So this is just to summarize this very, very surprising point. The refocused signal converges in probability to something which is perfectly deterministic and which is described through the convolution kernel, which depends only on this function v1, which depends on which contains the important information. So you can do this numerically. Pop. You take the previous experiment, you record the reflected wave, you send the recorded signals back into the medium, and you will get a perfectly coherent signal coming out of the medium. And this perfectly coherent signal, of course, is not the original signal. Here you compare the refocused signal with the original signal. You can see a deformation, of course. But you can see that here I have the results of 2 numerical simulations performed with 2 realizations of the random medium, and you get exactly the same refocused pulse. So it does not depend on the small-scale fluctuations of the medium. This refocused pulse is perfectly deterministic and depends only on the large-scale fluctuations of the medium. So just here to compare, these are results of the numerical simulation with the theoretical refocusing kernel. In this experiment, of course, I know everything. So I do not have to do imaging. Here I know everything. But now if you think about imaging applications, well, that means that all the information you are looking after is in V1. So what you have to do to get V1 is to do a series of time reversal experiments. You send pulse, you do this time reversal experiment, you compare the refocused pulse with the input pulse. This allows you to, by a straightforward deconvolution process, to get KTR, the convolution kernel. From KTR and playing with a recording time window, you get V1. And once you have V1, you have everything. So the problem we had in the previous slides, how can you compute the autocorrelation function, this expectation by local average and so on, is here completely solved. Actually, the medium has computed the autocorrelation function for you. Of course, the medium knows the medium, so it's perfect. You have nothing to do. The medium has done it for you. So just to conclude, so I've just shown you a couple of phenomena. I've just discussed a couple of phenomena in about wave propagation of in random media, but I want to stress that the most interesting stuff is coming from time reversal experiments, because actually you can see that you have this beautiful statistical stability, this perfect statistical stability that we only knew 10 years ago. I would have told you only the transmitted pulse has some statistically stable feature. Now we know that the reflected waves, these incoherent waves, and actually in 3-dimensional media, any scattered wave can be processed through a time reversal experiment to regenerate a perfectly coherent signal. So I have just shown you how you can use this time reversal experiment to extract information about the medium. And you have also applications to telecommunication. Oh yeah, in 3 minutes I can show you how it works. It's beautiful. It's the same as for imaging. It's just magic. Imagine you have two, I have, say, an emitter and a receiver. And the emitter wants to send a signal, what's the signal? F from E to R through a highly scattering medium. So highly scattering means that if you try to send F from here to here, what you get here is noise, completely incoherent signals, the same type as the one we had in the previous experiment. So you are doing a time reversal communication scheme. What does it mean? Instead of doing that, your receiver first sends some short pulse, say F naught. So this is F naught. This has nothing to do with F. So the receiver sends this short pulse. The emitter receives a noisy signal, so that I call G. What is doing the emitter is first to time reverse this G and to set it back into the medium. So send it back, it means blah, 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 blah. With, back. No, the converse. So if it is time reversed, say, okay, this time reversed signal is sent back into the medium. what R is receiving is, according to the time reversal theory, a current signal, the refocused signal. So what will receive R is F naught with some deformation described by these time reversals refocusing kernel. So that's the second step. And third step, your receiver is sending not G minus T, but G minus T convoluted with F, the information. And what R will receive is KTR convoluted with F naught, and the medium is linear, the wave equations are linear, so convoluted with F. So by a straightforward deconvolution, R can extract F. So you can communicate in a very disordered world. Nobody knows, this signal is completely incoherent. He does not have to know what is F naught, doesn't matter. KTR, you do not have to know it, you just deconvolute, you don't care about what is KTR. So everything is nice. So just to conclude, in June 2006, there will be an excellent book written by excellent people about this type of problems. And this is the end of my talk. Thank you for your attention.
Thank you very much, Josselin. We have time for a few questions. Yes, Claudio.
Yeah.
What are the size of the transducers and more or less the frequency of
It was done in ultrasound, so the mirror is very nicely sampled, lambda over 2. In this was in the three-dimensional world, so you have to deal with a mirror which has some spatial resolution, very nice spatial resolution, so you have to sample it at lambda over 2, lambda the typical wavelength of your pulse. So that, because you have to record the signal very precisely to do a time reversal experiment. You have to record the signal very precisely in the time domain and also over a small lateral spatial dimension if you are in 3D. In 1D, of course, you don't see it, but in 3D you will see it. And just in this experiment, I can't remember, it was ultrasound for echographic imaging. Let me see if I go back far, just here. What was the typical frequency? I think something like 20 megahertz. 20 megahertz, I think. And the wavelength was 3 millimeters. So this time reversal mirror is a device which is of that size, which consists of, there are different generations, but a few hundreds of transducers. Yeah. Nothing, because everything is in the phase. So, yes, this is an interference effect, actually. Everything has to be done in the, yeah.
Any other questions? Actually, Andre?
Maybe just one comment regarding the last experiment. You should say also that since you get refocusing in time and space,
it's
of
course.
Very safe communication, right?
Yeah. Actually, this has been done in ocean acoustics with a spatial resolution, which was simply amazing, I think. They communicate between two submarines at, with a distance of 40 kilometers, and the focal spot was 2 meters. You had a refocusing on a focal spot of 2 meters, and no signal out of this very nice focal spot. So you can communicate in a very secure way. Yeah. Yeah. Yeah.
But all this focusing back the case, doesn't violate some of this? Like we have this concept, we suppose, we focalize everything to the same point.
Yeah.
After all this,
Yes.
how does somebody lose weight when simply will get to this?
No, because maybe you are thinking in a classical world. If you think, for instance, at a billiard, you send a particle in a chaotic billiard after 100 reflections. you can tell, okay, if I send back the particle exactly in the exact opposite direction, it will do the back propagation and come back to the original point. Of course, this will never work because in a classical world, any tiny mistake you do in your back propagation and it's over. Here, you are more closer than, I would say, a quantum world or a wave world, and things are much more stable. For instance, you see this experiment, I've cheated a little bit, has been carried out for technical reason. What they send back is not exactly what they have received because they have done some numerization, and they have done what they called one-bit time reversal. That is to say, when they had a signal which was positive, they recorded 1, and when they had a signal which was negative, they recorded -1. And nevertheless, it works, and you can show it. What is important is the phase, not the amplitude. Because this is really, you have to think this is really an interference problem. So if you are wrong about the amplitude, it's not a big deal, but you have to be very precise on the phase, so you have to, here in that case, to detect very precisely the zero crossings. And if you have them very precisely, the back propagation is doing well, and the refocusing takes place.
If I may interject, perhaps it's a good moment to break. I just wanted to mention that the skepticism of Clodoaldo Ragazzo's now, it was the same that I had 5 or 4 years ago when I first saw these things. I must say, it's after you look at these things, you start getting convinced with the results. I think the proof is in the pudding here.
But it won't take you 5 years because now everybody.
Yeah, I'm slow sometimes.
It won't take you 5 years.
Yeah.
Well, perhaps we should break now and thank Josselin again
Thank you.
for the very